Right, let's take a look at this problem. Validate binary search tree. Given a root of a binary tree, determine if it is a valid binary search tree. So binary search tree is so left subtree contains only nodes that with keys less than nodes key, and also vice versa. And both left and right trees must be binary search trees. So uh, for For this, we can just use recursion because it's easy to check left and right. And I'm just gonna have a helper function. I'm gonna define a helper function that will take a root. This is helper function for recursing. So this will return. So if not root. If it is empty, it will return true, right? Because empty is the tree is a binary search tree, and it will return false if if root that we have it at this moment we have root, and if root left if we have root left and root that left yeah. If you have root left and root left value is greater than my root value, then return false. Also similar case with the right. All right. And but this should be smaller than or equal to, because right sub 3 is greater than less than greater than, then I just have to do it like this. And here I just want to check left and right subtree. So if there is a so I can simply just call the helper for root that left, which might be null, but in that case I just return true, and also helper root that right, and in that case I'll just return that. And since I need both of them to be true, I just because of this like a rule, we just want them to be both true, and for that we will just check it with this return statement. And here I'll just call the helper function with root, and I'll just return that. So let's take a look at this example. If the root is not root, it is not null, we just check if left is less than that. But so here we are missing one thing, which is that when we go right, we are, so let's say that we are going right to the tree, and then from tree to left we are going like -1. In that case, this is not binary search tree, and we have to hold this, pass this 2 to the child node, so that every time we make sure this left subtree of elements in this side will have values greater than the minimum value we pass from the parent of that tree. So for that I have to pass them parent like minimum and maximum, like that. And I just have to make sure that at this at the start. So minimum is float infinity, so that will just, it can be anything. So wait, it can be, wait, from it as just 1 second. So I will determine that just in a second. Yeah, it should be negative infinity and this should be positive. So at the start, our range is from negative infinity to maximum infinity, and we'll just check it here. So if the value current left is less than, so here instead of checking from the roots to left, here if we have a root, we just check if this is less than, so root, we have root left, it should be less than, I mean greater than the minimum. Let's see. So if it's greater than minimum, we return false, and right is smaller than the minimum, because right should be greater than the minimum. Let's see. Yeah, these are correct. And if we go left, we have the minimum should stay the same, but the maximum should be root that value. And here the root value, we pass it as the minimum, because when we go right, we have to pass this 2 to right subtree, and it will use that minimum in the left subtree of that tree. And here we will pass the maximum there. So at the start, when we go left, we just pass here minus infinity to 1. We pass minus infinity and also 2. And when we go right, we pass 2 and infinity. And this we will just go to 1. In that case, the root, do I even need this? Root right, root left? No, I don't need this. Root that value. I also made a mistake there. So that value, so if root value is between these, I can also carry this to here. If these are the cases, it's all right. But if it is not that case, we'll just return false. So at the start, the root value is not greater than the infinity, not less than minus infinity. We just go left, and for left, it is in between minimum, which is minus infinity, maximum is 2. This will also won't go in this, and then we go left and right of subtree of that, and what will happen is that we will just return true in those cases. A similar thing will happen in the right subtree, so this should be this should work. And here also with the recursion, we just ensure that it goes on, and every left subtree is binary search tree, right subtree is binary search tree, will return true. If this is the case, we just return false, just recursing back and always returning false because we have an end here. So let's check if this works for the test case, and let's submit and see. So we have a problem here. It is returning true, but it should return false. And is this because of the equality here? Oops. So it should be 2, 2, 2, should not be false. And then yeah, okay, it is less than equal to. So if these are the cases, it should return false, right? I forget about those because I'm doing a like reverse like less than is greater than equal to the opposite of less than is greater than equal to. So okay, it is accepted. What's the complexity here? We just go over every node in this binary search tree. So number of the time complexity is number of items, and the space complexity is the depth of the tree. So like this, which can be at most n of n, but depth can be less than n. So I'm just gonna write it like this. So yeah, this is my answer to this welded binary search tree problem.